Good morning. This lecture presentation will be covering resonance and formal charges. Resonance occurs when one Lewis structure cannot accurately depict a molecule like ozone. We are able to use multiple structures, which we call resonance structures, to describe the molecule. You can see that with the colors at the top, that when you mix blue and yellow, it creates green. So a resonance hybrid is a mix of the two molecules together. The electrons are not just simply moving back and forth, it's just a blend of those two different structures. You can see with the resonance structures for ozone underneath that it can be depicted by more than one valid Lewis structure, best represented as a resonance hybrid. So the resonance forms are not real bonding depictions. O3 does not change back and forth between its two resonance forms. The real structure of the resonance hybrid for O3 is an average of its contributing resonance forms. If you recall, bond order is determined by the number of electron pairs between two atoms divided by the number of bonded atom pairs. In the case of resonance structures, they often will have a fractional bond order due to the partial bonding that occurs between the atoms. So for O3, the bond order would be the 3 electron pairs, the 3 bonds that we are making on the molecule, divided by the 2 bonded atom pairs. So 1.5 would be the bond order for the oxygens in ozone. As a quick analogy for resonance, we can look at the creation of a mule. A mule is a genetic mix, or a hybrid, of a horse and a donkey. If I mix a blue horse and a red donkey, I will get a purple mule. It is not a horse at one instance and a donkey at the next. It is a mix of the two, and it is permanent. Likewise, a resonance hybrid has a single structure, although it retains characteristics of its resonance forms. One of the most important organic molecules is benzene, C6H6. It has 2 resonance structures shown to the right. You can see that it has an alternation of single and double bonds, where you have the double bonds simply shifting its position throughout the molecule to form the other resonance form. It is commonly depicted as a hexagon if we use that line angle formula that we learned earlier in the year, with a circle inside to signify the delocalized electrons shifting between the different carbon atoms. The localized electrons, which would be your sigma bonds, the ones directly between the 2 nuclei of the carbon atoms, they're going to either be specifically held onto by one atom or shared between 2 atoms. The delocalized electrons, again, the pi bonds, which are going to be an overlapping of some of those p orbitals, they are going to be allowed to freely move, thus delocalized, and not held onto by a specific atom. So they have the freedom to move throughout the structure. So let's now take a moment to go through and actually write out the resonance structures for the nitrate ion. And we're going to find the bond order. So when we start off with this, we need to get our Lewis structure. So I'm going to go back from our last video and let's set up our Nasser to figure out the structure. So again, in this situation, I'm going to put a minus over here for the charge. So that way we remember to use that electron. So neither nitrogen or oxygen represents an exception. So I'm going to have 8 electrons for the nitrogen. I have 3 atoms of oxygen. So I'd have 24 electrons total. For the number of needed electrons, the charge does not come into play, so I'd have a total of 32 electrons. For my available, nitrogen has 5 valence electrons, each oxygen atom has 6, and so that will give me a total of 23, but then I have the extra for the charge, for the 1 electron, and so that will give me a total of 24 electrons available for bonding. For my shared, remember we take the N minus the A, so that is going to give us 32 electrons minus 24. So that tells us that we need to share 8 electrons, which if we divide by 2, that tells us that we need to form 4 bonds. And then for my remainder, A minus S, we're going to take the 24 electrons that we have available, we remove the 8 that we use for bonding, and that tells us that we have 16 non-bonded electron pairs that will be out there. Now, when we are looking at our structures, again, I will have the nitrogen in the center because it's the least electronegative. I have 3 different oxygen atoms, And you notice we need 4 bonds. So again, we're in the situation where just having the 3 atoms singly bonded, we need 1 more bond. So we're going to arbitrarily choose one of those oxygens to have a double bond. So now for my structure, the nitrogen has 8 electrons surrounding it in terms of the bonds. Each of the singly bonded oxygens only has 2 electrons, so each one would need a set of 6 electrons on the outside. There are 12 of our 16, and then the double bonded oxygen is sharing 4. So again, we will have 4 electrons on it to give us the total of 24 available electrons. To represent a resonance form, what is going to take place is we draw a double arrow to represent the resonance between the structures, and you would have the electrons from the double bond basically shifting out into the orbitals for the oxygen, and then one of the sets of lone pairs on another oxygen can shift down to the nitrogen to form another bond. So I'd have the nitrogen again, and this time I'd have the double bond coming to the oxygen on the top, and I would have still the 6 electrons on each oxygen that is singly bonded, and 4 on the oxygen that is double bonded with the negative charge. And I can have one more where the electrons will shift back up over to the oxygen, and one of the other lone sets will shift down to the nitrogen to double bond, and that will give us one last structure for the nitrate ion, which will be the single bond, and double bond on the right, with that minus charge. So for the bond order, again, we look at the number of electron pairs that we have. So for the bond order, for the nitrogen, or the nitrate ion there, I have 4 electron pairs. And if you notice, I have 3 different bonds between the nitrogen and oxygen atoms. So I have 3 bonded pairs of the NO bond. So my bond order would be 4/3. Formal charge is the charge of an atom would have if all the electrons were shared equally. It gives us an idea of which of the different resonance forms would actually be the most probable for a molecule and would contribute to the greatest characteristics of the structure. The formal charge of the atom is equal to the number of valence electrons minus the number of unshared valence electrons. These would be your lone pair electrons, non-bonded electrons. And then technically it's 1/2 of the bonded electrons, or the shared electrons. But since each of the different bonds that are created share 2 electrons, it's just easier to say the number of bonds. So I'll use that as my reference, but again, you won't see that in your textbooks. We're going to look at the example for the ozone molecule, and we're going to look at structure number 1, and we're going to focus on the oxygen that is labeled A. In this structure, the formal charge for oxygen would be equal to, again, the number of valence electrons, which would be 6. The number of lone pair electrons. So if you notice, I have 2 sets of lone pair electrons, so I have 4 unshared electrons. And then because I have 2 bonds, they would be sharing 4 electrons. 1/2 of 4 is 2, or again, just 2 bonds being present. So 6 minus 4 minus 2 equals 0. Okay, so figuring out which is the most important resonance form is pretty simple. When you have looked at all of your different molecules and you have assigned them formal charges, the key thing that we want to have is the smaller formal charges, positive or negative, are preferable to larger ones. The resonance form that contains the greatest number of formal charges equal to 0 will be the most desirable. The same non-zero formal charges on adjacent atoms is not preferred, so meaning that it's not good to have 2 sets of negative numbers for the charge or 2 positives. You don't want to have the charge distribution being the same. The molecules, if it is a neutral substance, the formal charges should add up to equal 0. If it is a polyatomic ion that you are looking at, then the formal charges should add up to equal the charge on the ion. Now, as a tiebreaker, if you have multiple structures that have the same number of zeros, then the more negative formal charge should reside on whatever atom has the greater electronegativity value. Okay, so let's look at a quick example here to assign our formal charges. So we're going to focus on the POCl3 molecule. So again, the first thing that we're going to do is draw some of the possible Lewis structures for this. So start off again using our Nasser method. So I have PO and Cl. It is a neutral molecule, so all the formal charges should add up to equal 0. I have a set of 8 electrons each for phosphorus and oxygen, and I have 3 times 8 electrons for the chlorine. So I have a total of 40 electrons that are needed. When I look at my available, I have 5 electrons for the phosphorus, I have 6 electrons for the oxygens, and I have 3 times 7, or 21 electrons for the chlorines. So this will give me a total of 32 electrons. For my shared, again, I will have the 40 electrons from the needed minus the 32 electrons that are available. So I'm 8 electrons short without bonding, so I'm going to share 8 electrons, so that would mean I have a total of 4 bonds. Now for the remainder, again, I would take my A value, which was 32, and I would subtract the 8 electrons, so I'd have a total of 24 electrons remaining. So when we look at our first resonance structure, again, I would have single bonds to each of the oxygens and the chlorines. I'm choosing phosphorus as my central atom because, again, it's the lowest in electronegativity values. And now each of my bonds to chlorines or oxygens only have 2 electrons, so I'm going to need a total of 6 electrons around each of my different chlorine and oxygen atoms. The phosphorus, having the 4 bonds, already has 8 electrons, so it's good. So now when we draw our resonance form, you might be sitting there going, wait, why is there a resonance form? Please remember, like I had mentioned in class, the set of elements, carbon, nitrogen, oxygen, phosphorus, and sulfur. These are your elements that have the tendency to form double bonds. So one of the things that we can do, notice chlorine is not on that list. So one possibility is I can have this set of electrons come down from the oxygen and bond with the phosphorus, and that will give us this structure as our second resonance form. Add in the electrons here, and now we're ready to do our evaluation. So again, we have our number of valence electrons minus our number of lone pair electrons minus our number of bonds. Okay, so looking at structure number 1, if I'm dealing with the phosphorus, again, it has 5 valence electrons, it has 0 lone pair electrons, and it has 1, 2, 3, 4 bonds, so it will have a formal charge equal to +1. For each of my chlorines, notice in this instance that my chlorine atoms are all identical, so I can look at each one individually and just multiply it by 3. So I have, in this case, 7 valence electrons. I have 2, 4, 6 for my lone pair electrons, and I have 1 bond. And so 7 minus 6 minus 1 is 0. So again, since I'm multiplying that by 3, 3 times 0 is still 0 anyway. And when I look at my oxygen atom, I have 6 valence electrons, I have 6 lone pair electrons, and I have 1 bonded electron coming from the oxygen, or 1 bond. And so 6 minus 1 gives me a -1 charge. Notice +1, 0, and -1 adds up so the molecule equals 0, so this is a valid Lewis structure. When I look at my second example over here for structure number 2, do the same thing, P, Cl, and O. Notice again my chlorines are all the same. The phosphorus here, slight difference. I have 5 valence electrons, I have 0 lone pairs, and this time I have 1, 2, 3, 4, 5 different bonds. Again, the double bond counts as 2 bonds. So I would have 5 minus 0 minus 5, which would give me 0. The chlorine, again, multiplying that by 3, I have 7 valence electrons, I have 6 lone pair electrons, and I have 1 bonded electron pair. Half of that would be 1, so 7 minus 6 minus 1 would also give me 0. And then finally for my oxygens, if you notice, I now have a double bond and I have 4 lone pairs, so I can subtract the 4 electrons that are the non-bonded, and then I can subtract the 2 bonds. So 6 minus 4 minus 2, that would be 0 as well. So as you can see in this particular example, because my formal charge adds up to 0 for the second structure, it is also a valid resonance form. So to determine which one is best, again, I'm going through my rules. The structure that has the greatest number of zeros, in this case my double bonded phosphorus oxygen molecule, is going to be the best structure. So this will be the most likely resonance form, greatest contribution to the structure of the molecule. So that wraps it up for this particular video. There will be one coming on the VSEPR theory and hybridization next, and that should get us through for our test. I'll also start doing some videos on free response questions from recent AP exams to help you get prepared as well. So look for that coming soon.